Okay. Cool. All right, well, if we're ready to get started, then let's get going.
Yeah, so, do you need to click anything or?
No, just you can do it.
Yeah, so our group's called Ptolemy Solutions. I am Joshua Cotton, and that is David Watt. That's Giovanna. This is Elisa right here, and that is Alex. And here's our project. Okay, here you go.
Okay, so this class consists on designing a solution for lunar regolith. So this is the dust that covers the moon. It is the result of billions of years of bombardment of meteorites. It is a chemical makeup of lunar bedrock, then the meteorites, and then some rare metals. So it is it has the grain size between 60 and 80 micrometers, but there's also big boulders and really tiny particles that are nanometers in size. Since there's no weathering processes in the moon, these particles are very sharp and abrasive, which is one of the biggest complications of this material. Mm-hmm. So it causes several negative effects. One of them is this material sticks to surfaces in the lander, sensitive materials such as the thrusters, cameras, sensors. It messes up navigation systems. It is really hard to get rid of. And it also sticks to the astronaut suits. When they do EVAs, they get the particles into the lander and then outside, and it's a mess. So, okay, so our objective is to find a solution. And then we picked one target. Our target is reducing the air density of regolith in the lunar atmosphere. And how we decided to do that was by modifying the lunar surface, which we will explain the solution later. Okay, so for these Artemis missions, these are the ones that are taking rockets and spaceships to the moon. We had to pick a lander, and we had, well, a spaceship. We had the SpaceX rocket and then the Blue Origin lunar lander. We went for the Blue Origin lander because a few different reasons. This one is inside the New Glenn rocket, so our design wouldn't be in contact with the Earth's atmosphere, which is one of the positive aspects of it. It's also smaller, the thrusters are weaker, the missions are simpler, it's just an easier choice for us. Okay, we decided on some design goals. The first one was a budget increase of 5%. The lander is roughly 3.2 billion. So that would give us $160 million to work with. Then we went for a decrease in 5% of the payload capacity, which is 5% of 20 tons is 1 ton. It had to be ready in 3 to 5 years. The technologies must be already available and developed, versatile, sustainable. It should survive many ascents and descents. It should be, hopefully, could work for more than one lander, and then easy application. If the astronauts don't have to interfere with the system, would also be ideal. Okay, so this is the design we came up with. We called it the LSPS, the Lunar Surface Preparation System. It consists of 2 parts. It's the railing and the capsule. The railing, it's the part that contains the capsule. It will guide it down, and it's the one that's attached to the surface of the lander. And then the capsule is divided between 2 chambers. The top one is the one that contains the tarp that we will release, and then the bottom one is like here. and it's pressurized and it has a wheel lock mechanism. This is the one that's designed to deploy the capsule.
All right, so the concept of our design is relatively simple. There's going to be two stages to this, the release and the deployment. So we have two of those railing capsule systems mounted to the side of our lander. Once it reaches about 100 meters off the surface is when they're going to be released from those railings, and they're going to enter into a free fall towards the lunar surface. Once we reach, then the next stage is the deployment phase, where these tarps are going, or the capsules are going to open up our tarp fully expanded so that they land on the lunar surface and give us our lander some sort of like landing pad for so it doesn't kick up as much regolith. As you can see by this graphic on the right side here, the blue circle is our land itself, and then the tarps are the squares around it. So our goal is to cover as much surface area as possible so that the exhaust doesn't kick up as much. You can see it by the graphic there. Go to the next slide. So our dynamics here, like I said, the capsules are released 100 meters above the lunar surface. So that gives us enough so that these capsules can get out of the influence of the lander itself and the exhaust by the time it makes contact and deploys. Once these capsules enter free fall, it will take around 11 seconds for these capsules to make contact with the surface. So we decided to deploy the tarps and the capsules 10 seconds after it's released. So it's about 20 meters above the surface, which means it'll be outside of the influence of the exhaust itself. An onboard computer on the lander is going to control all stages of this to minimize the complexity for the astronauts. Once the altimeter or the lander knows it's about 100 meters off the surface is when it's going to do that staggered release of both capsules. And then after 10 seconds, it's going to activate our motor within the capsule to fully deploy. So the capsule itself is divided up into 4 quadrants, which we'll look at later. But the idea is that each one is deployed into equal and opposite directions, and it drags out the tarp behind it. So these quadrants will deploy at 7.5 meters per second, which is half the diagonal length of the tarp itself as it goes in opposite directions. So it'll reach a full expansion after 1 second. That's that final second of its free fall. So once it's fully expanded, it'll hit the ground, and those quadrants will act as anchors for our tarp, and it'll have full coverage. And then the lander itself is still going to be around 90 meters above the lunar surface when these capsules land, so that the exhaust doesn't have any kind of effect on the dynamics of the deployment either. Next slide.
Okay, so now we're going to take a closer look at our capsule itself. The capsule is made of aluminum 7075 T6, which we selected due to its high weight to strength ratio. The capsule is divided into 2 chambers, an upper chamber and a lower chamber, as well as being divided into 4 separate quadrants. So the upper chamber is houses the zirconia fabric tarp, which is hooked onto each one of the 4 quadrants using hooks. And the lower chamber is pressurized and houses a wheel lock mechanism, which we use to eventually deploy the capsule and the tarp. So now we're going to take a look at the interior of the capsule. Like I said earlier, the capsule is divided into 4 separate quadrants. They're all in equal size. At the top of each one of the quadrants, there is a tarp hook onto which each one of the 4 quadrants, each one of the 4 corners of the zirconia fabric tarp, they hook onto these hooks at the top. The capsule is a total of 1.08 meters high and 0.44 meters in diameter. We're going to go into this a little bit more later about why we specifically chose 0.44 meters, but it is to fit within the requirements of to ensure that we still fit inside of the New Glenn rocket, since these 2 capsules are going to go on the outside of the lunar lander. And again, the tarp is stored in the upper chamber and the lower chamber is pressurized. So here we have the actual tarp that we're going to use, which is going to be made out of zirconia fabric. Zirconia fabric was selected due to its high temperature resistance properties. The Apollo lunar lander exhaust was measured to be about 2,500 degrees Celsius, while the melting point of zirconia fabric is 2,715 degrees Celsius. which would ensure that we would at least to some extent be able to withstand the heat of the exhaust as the lander is landing down onto the deployable landing pad. I know you might be wondering if it's going to be, releasing some type of toxic fume, but it will not. It does not release pollutants at high temperatures. The density of the tarp is about 80 kilograms per meter cubed, which would ensure that it's not easily uplifted by some of the upheaval of the lunar regolith or anything like that, and that it's more durable. The tarp size is about 10.6 meters by 10.6 meters by 0.9 millimeters. We're going to go into this a little later in one of the other slides of why we specifically selected 10.6 meters as our length and our width, but it's to ensure a coverage that we calculated based on previous lunar landings. The usually typically heavy duty tarps are about 0.5 millimeters thick for any other type of material, but we made our tarp 0.9 millimeters thick, which is almost double that, in order to ensure that it is durable and that it won't like rip or easily become destroyed. And the tarp in total, there's two tarps, one on each side, and together like they partially overlap in the middle, which is where the exhaust would be like the most intense. But together, when they're both on the ground, they would cover about 16.2 meters by 10.6 meters, and the tarp in total is about 9 kilograms heavy.
All right, and now we'll take a closer look at that wheel lock mechanism, which is in the lower quadrant, which is responsible for that second stage, the deployment phase. So it consists of a fully detachable system with the base plate, the wheel lock, the motor, and the batteries. As you can see by this graphic here, that wheel itself is the wheel lock, and I like to think of it as the child lock on a medicine bottle, where you have these interlocking pins, and then it rotates to lock them into place. So the idea is that this lower chamber is fully pressurized, and that once that wheel lock system rotates upon deployment, that the pressure will take over and then push these quadrants in the equal and opposite directions. So, and by it being detachable, we wanted each of those quadrants to be equal in every way. So the wheel lock mechanism itself is just going to go into a free fall and fully detach from the rest of the system once it's activated. Just to release it, it's just a 10-degree rotation causing that separation. Once the pins are free, the pressure again will take over and deploy our capsules. Next slide, please. To arrive at our pressure, we did a little bit of analysis. We did a momentum analysis here. Like I said before, the main design goal was that velocity of deployment, which is 7.5 meters per second, which we arrived based off the size of the tarp itself. So we used simple momentum analysis here. Mass times velocity equals the impulse time times the force. And then the force is obviously a result of the area and the pressure that is affected. So the mass of a fourth of our quadrant is one quadrant itself, and then a fourth of the tarp, which will be pulling behind it. It came out to be 14.75 kilograms. The area that we're concerned with is that inside wall of the lower quadrant itself. The top and bottom are going to cancel each other out, so we're only concerned with that outside wall, about 0.066 meters squared. And then our impulse time was chosen to be 0.1 seconds. And then after all this calculation, we came to a pressure of 16 kilopascals within that lower chamber. This is the pressure differential between the outside and the inside, but the moon has a negligible pressure, so that's just the pressure within our capsule. As you can see, I said the impulse time needs further testing because that's the time it would take for that lower quadrant to fully depressurize, which we chose to be 0.1 seconds for this calculation, but in reality, it could be larger, smaller. If it were to be smaller, then we can get away with a larger pressure and make that a bit more manageable when we come down to our thermodynamics of our design. And then going into a gas analysis, we chose it to be air because it didn't really make much of a difference when you chose different gas. So we have 4.5 moles of air within that lower chamber. And at our pressure, the calculation results in about 50 Kelvin that we need to maintain to keep our design pressure of 16 kilopascals.
All righty. So y'all heard a little bit about the capsule itself. Now let's talk about how we actually get it to the lunar surface. So a close look at the railing, you'll see consists of 4 legs, so the top and the bottom here. The top component of the railing contains our mechanical or our mechanism here, which we'll get into later, which pretty much involves two clamps that are then driven apart by two opposing step motors. These motors will then incrementally push these linkages further inward, which I'll share in a little bit. But overall, the railing, it's aluminum 6061. It's going to be assembled using blind rivets. That's going to be for all the joints that connect different components of the railing. In addition, and it's also going to contain the railing where the railing connects to the lunar lander itself. Can we go to the next slide, please? Awesome. So regarding that attachment itself, we did a little bit of analysis on what's the chances of any of these pins, these rivets failing in shear. Pretty much what we took a look at is during vertical ascent, lunar lander is going to be under its most amount of stress. That's going to be a shear of about through 3.21 Gs, pretty much the acceleration of the rocket while it's ascending, carrying the lunar lander itself, and therefore carrying our design. So pretty much we came out to a shear margin of safety of 4.52. Now this is for each individual rivet and whether they would actually shear. So at least in that sense, this design should not be going anywhere. Now, just because the pins don't move doesn't mean we may not have buckling. So we decided to take a look at some buckling. How I went about this is I divide each of the individual panels into 7 equal sections. Each section is going to have 4 rivets essentially. And pretty much what I looked at buckling in the vertical direction. So I did assume that the sides would be fixed. And this is mainly because if you take the entire plane as a whole, so in this case, highlighted in green, comparatively, you're going to have fixed ends just due to number of rivets as opposed to the top and bottom. So I did make that assumption there. But under that assumption, it came out that we had, when given the max shear, which is caused by that same force of gravity, I pretty much use a critical buckling shear. We modified the equation to account for this being a actual sheet of metal and not just a regular beam that has buckling. And the margin of safety that we get from that is 12.8. So in theory, there should not be much vertical buckling going on here, if any, hopefully. Looking at the release mechanism itself, so I said a lot of words a couple slides ago. This is a more in-depth picture of what that actually looks like. Each step motor is going to be programmed to move the linkages, which are highlighted in red. Those are going to be moved linearly down a shaft, down a threaded rod. And that is what's actually going to push the clamps apart or pull them together. Now, if you look at the right, you'll see that each clamp has an insert for two opposite tabs on the actual capsule. You can see the tabs on the bottom right photo. Now, these tabs are designed to be completely flush with those inserts. And then when we move the capsule apart, you're going to see that the tabs should be able to fall through 2 opposing slots that go along the railing, meaning that there should be very minimal spin of the capsule while it's being dropped. And on top of that, it should be able to be dropped fairly cleanly once the clamps are separated. Now, a closer engagement on that vibration. I was not very worried about lateral vibration, which in this case, vertical being the direction in which the capsule is dropping. That was because the capsule itself is completely concentric and flush with the sides of the railing. The railing itself is about 1.17 meters, which means we're getting at least 1 meter of length that's going to be flush with the capsule itself. Furthermore, when the clamps remove, essentially, I'm not worried about horizontal vibration. However, vertical vibration is a real thing to worry about. So I took a look at each of the tabs, which you can see on the top right again. Essentially, what I did is I simplified each tab as its own cantilever beam. So pretty much what I did is I took the arc length divided by 50 as it's 50 degrees. That's what we're dealing with anyways. So I was able to take a look at that, work with the dimensions there, and I came out with a whopping margin of safety of 149.9. This is using the same forces of that 3.21 G. So once again, during the entire life cycle of this product, it should never go through more stress, at least vertically speaking, than when it is initially being launched from Earth. And that's because the gravity is lower on the moon. And that is also due to the thrusters generally being weaker on the lunar lander itself. So this margin of safety is very high, perhaps too high. But again, the goal is to make sure that this capsule is not moving without our input, without the clamps being separated. And to ensure that movement, we want to make sure that margin of safety was very high.
Yeah, so following that similar logic, when you look at the structural analysis of the hooks that actually hold the tarp to the capsule, it's going to experience the most stress during liftoff as well, because it's going to experience that 3.221 Gs of acceleration. So these hooks, they each hold about a fourth of the tarp's weight because there are 4 of them. And when you look at the normal stress and the stress due to bending that the hook or sorry, that the tarps put on the hook, you get a total stress added of about 20.64 megapascals. Now, the hook is assumed to be fixed to the top of the capsule, and it is made out of aluminum 6061, which has a yield strength of 241 megapascals. Now, the target factor of safety for yield is 1.15, which leads to a margin of safety of 9.15. So these hooks are very comfortable with handling the tarp's weight under the acceleration of the rocket. Next slide. So now looking at the thermal analysis, just to note, the work due to the ATO BLDC wheel lock motor, which is powered by 2 UB 1290 12-volt batteries, that work in the thermal analysis is very negligible because it's only 0.4 joules. And in order to solve this thermal analysis, we need to calculate the equilibrium of the outer surface temperature of the capsule. So when you look at the equilibrium, you have the heat coming in from the sun due to radiation, and that is a function of solar irradiance and area. The solar irradiance is taken to be at its maximum when Earth is in perigee and the moon is at its apogee point, which is about 1,400 watts per meter squared. So that is the heat coming in, but there's also 2 components of heat coming out. You have radiation from within the capsule itself, and you also have conduction from the inner chamber to the outer chamber. And T1 is the outer surface temperature, and T2 is the inner surface temperature. And at equilibrium, you have about 1275 watts coming in and 1275 watts coming out, which when you solve for the outer surface temperature, which is the unknown variable, you get about 50.109 Kelvin. So essentially what all this is saying is that due to the solar radiation, it's only going to heat the external wall to like 0.1 more Kelvin than it is in the inside. And this is because of the extremely low emissivity of the aluminum material. 0.15 is actually that's actually an overestimate. And what essentially this means is that the aluminum is terrible at keeping out heat, but it's also terrible at keeping in heat. So whenever you drive this to equilibrium, the inner temperature and the outer temperature actually don't change much because the exchange of heat is very similar. So therefore, we actually need no insulation. If we had insulation, this would actually trap heat. So it's actually better to not have it. Next slide.
Cool. So now a little bit to talk about, whether this design can actually work. So what you see here on the left, this is pretty much the blue is going to be the lunar lander. We estimate about 5 meters in diameter. 16.3 diameters is the green, which extends around it. This essentially refers to the width of the kick up for the regolith during descent. Apollo astronauts originally cited that from about 100 feet up, that they could start seeing regolith already at their window. So pretty much it gets kicked up that high from that high up. So essentially, I did some math here. I transplanted the mass, the total mass being kicked up normally from a regular landing without our design. I went about 7 centimeters deep. This is only accounting for the most loose of particles, mainly because when astronauts originally were stepping onto the moon, their footprints were about 7 centimeters deep, 5 to 7, so max of 7. So taking the lightest regolith, the one that would most easily kick up, I calculated the mass that's being kicked up, and then even divide that out to look at, let's say if we had a completely even distribution of that mass throughout that entire green volume on the left, it come out to about 49,000 particles per meter cubed, per cube meter. Now, of course, this distribution is not going to be even. However, the point was in this exercise was to make that assumption just to clearly showcase that when we do add our tarp, and when we do prevent the tarp's surface area's amount of regolith from being kicked up, we then only end up kicking about 8,000 particles per cubic meter, which means that we end up decreasing the mean contact rate between regolith and the lander by 82.8%. Now, once again, these are estimates, and this is taking a lot of assumptions into account. Unfortunately, we don't have time to do a proper simulation, but just due to this, I think we're all very happy with that, provided the tarp can maintain its structural security during descent, which we believe it can. And there's a lot to be gained from reducing the regolith contact with this lander.
So really quickly, let's just do the overall mass and volume breakdown. So the railing system by itself is roughly 93 kilograms. The capsule is 61 kilograms, and that consists of three parts. The shell by itself is 50 kilograms, so which means each quadrant is about 12.5 kilograms, which is what we are using to weigh down the tarp. The tarp itself is 9 kilograms in total. And the wheel lock that holds the tarp, that holds the capsule together is about 1.65 kilograms. So the total mass per individual system, so that would be for one of these, is 154 kilograms, which means obviously when you double it, we are adding a total mass of 308 kilograms to the Artemis mission. The overall size of our system is about 1.6 times 1.6 times 1.6 meters. And as you can see in this chart over here, that gives us a clearance on each side of about 1.27 feet. So it does fit within the New Glenn rocket, as you can see here. Next slide, please. And then just to quickly sum it up, with our total mass being 308.74 kilograms, that is about 1.5% of our payload capacity, which is well below our goal of 1,000 kilograms or 5% of the payload capacity. So the total cost in materials is about $22,000. This is not factoring in labor, but considering that is a tiny fraction of our $160 million budget, I'm sure that labor costs would not increase it over that mark. And then a couple other goals that this reached is we were able to find a material, the zirconia fiber, that upon being heated, it is not toxic to the astronauts. So that's obviously a good thing. And our design overall, it doesn't use like too far out there technology. So this whole design is definitely attainable to make within 5 years with our current technology. And yeah, that is our whole design. Thank you guys for listening. And if you guys have any questions, just go ahead and unmute and we'll address them one at a time.
I think I'll let Rick kick things off because he hasn't seen this before, so I'm interested to hear his thoughts.
All right, sounds good.
So I just want to make sure I understand. So the goal is to keep cost underneath 160 million, and your cost came in at 21,865.
Yeah, yeah, so our total cost was based on just like the raw materials only, and that is per model. Yeah, that's only for one system. Actually, I think it was for two. Yeah, yeah. Yeah, so that is our total cost. So each system, so we have two railings and two capsules and everything contained therein. That costs about 22,000.
Okay. And then go back just a couple of slides.
Sure.
No, just one, sorry. Just
Right here.
yeah. So just I was joking with Tom about this, but just be careful going back and forth inches and meters, right? The two difference. I know you're just trying to give perspective on things, right? But
Right.
this is what gets people in trouble, right? Especially NASA with going back and forth between measurement systems. So I would just try and be consistent and just show one or the other and not both. I understand what you're trying to do here, but I think it can be confusing.
Okay, yeah, noted. Thank you.
And then if you go right where you introduce the zirconia fabric, like right at the beginning.
Like the material properties?
Yeah, yeah.
Yep.
So you mentioned you went with 0.9 millimeters thick instead of the typical 0.5 millimeters thick. Oh, what was your analysis in order to make that call?
Yeah, so it's actually the part of it that is being exposed to the exhaust is actually going to be 1.8 millimeters thick total because once again they overlap.
Okay.
And our analysis, we had trouble doing the exact, thermodynamics, trying to figure out like like based on how much heat exposure over time, what's the integrity of the material.
Yeah.
But yeah, sure.
I would say I don't want to do that analysis.
Yeah,
I would say one other concern was also manufacturability. 0.5 is typically what you're going to get for just regular, tarps used in everyday camping and such like that.
Mhm.
And so for the sake of transferring that, we wanted to be able to bump that thickness up to something that would be effective, but not so much so that it becomes more difficult and needs whole new ways of and just increases manufacturability by that much time.
Okay, and
So
as far
would you characterize that as just sort of eyeballing a number then?
Yeah, so I would say so. Yeah.
okay, and do you know specifically that that is manufacturable in that size? I mean, like how is it going to be made?
That's a great question. Yeah. Perfect.
The like size wise, yes. Thickness, maybe it should be like stick together.
Do you know like how it's actually manufactured?
I've researched that it is possible.
The reason I was asking is like getting back to your cost, right? So how do you arrive at your cost if you don't know who you're going to go purchase the 0.9 millimeter thick tarp from? I guess is what I'm leading to.
Okay, we didn't use that thing, but
Sorry. I think we didn't eyeball like the thickness specifically. We calculated like how thick it would we use like the previous Apollo landings to see how long it takes them to land approximately. And then we used that amount of time and the amount of heat from the exhaust that's being applied to the zirconia to see how thick it would need to be to withstand those temperatures at that amount of time without obviously its heat resistance is 2,715, but it obviously begins to degrade around that temperature and a little bit before that, like loses some of its, properties. So we just wanted to make sure that we didn't include those equations.
So it was more a thermal analysis than anything else.
It was a thermal analysis. The 0.9, it needs to be 1.8 millimeters thick in the middle, like around exactly where the exhaust is. So we made them 0.9 millimeters thick each. And then when they overlap in the middle, it's 1.8. But it is based on a thermal analysis.
Okay, all right, thank you.
Yeah, and then another point, there were a lot of factors going into this tarp size. One of the other factors was like, we needed to have a total tarp size, like the volume of it that's actually reasonable for us to fit into the capsule. So that's aside from the thermodynamics of it, but that was also another factor. But the width and like the tarp coverage on the ground, we did that based on the contact analysis that David presented, where roughly speaking, given a even distribution, we decrease it by about 80%.
Okay. And then when you actually have the tarp deploy, how do you guarantee that it deploys uniformly?
So in that deployment stage of our capsules, it's we're using pressure as our force to deploy this capsule, and pressure applies to all surfaces equally. So that's how and also that deployment mechanism itself is fully detachable. So all four of those quadrants are symmetric in every way. There's nothing, mass is all the same, shape the same. The pressure is acting uniformly on all four surfaces of that lower chamber. So once it's deployed, the wheel lock mechanism opens up. All four quadrants are going to be deployed equally in opposite directions, just based off the geometry and how pressure works itself.
Okay, so is the assumption that you're landing on a completely flat surface, or have you accounted for a non-uniform surface?
So I mean, if there's like micro irregularities, like a small divot or anything like that, I mean, the tarp is flexible itself, and that deployment phase happens mid-air, so it'll land on top of whatever is going on the surface. If it were to be, the landing site would hopefully be pre-chosen and it wouldn't be on the edge of a crater or anything like that. But if there's anything like some small rocks or dips or a little mound or something, then our tarp will be able to cover it, no problem.
Okay, yeah, I was just the recent landing on the moon where the thing fell over on its side. That's all I was thinking about. I will say a couple of things that I appreciated compared to presentations I saw last year. I was able to digest this as you presented. Last year, I felt bombarded by slides. So I really like the way that you guys have split up the presentation and made it digestible so that it could be easily followed. So I'll turn it over to Tom now.
Thank you.
Thank you.
Thank you.
Hey guys, so I'll start with the structure stuff, and I'll say that I appreciate you guys including the buckling calculations. Rick and I am back and forth during these a lot. Sometimes we're making fun of you guys. Sometimes we're saying, "Wow, what a good job." So this is one of those "Wow, what a good job" slides. I appreciate you taking the advice to heart from last month. Aerospace structures tend to fail in buckling. That's because they tend to be thin structures and under compressive loading. So that's the right kind of analysis to be doing without getting into whether the analysis is covering every failure mode.
Sure.
I think there's more that can be done here, but I think you're on the right track, and I appreciate you considering that. So good job there. On slide, let's see, 18 and 19, continuing on the structural analysis theme. All right, so maybe 17 is the right place to look at this.
Oh, 17?
Yeah. Okay. Yeah. Okay. So you've got two motors here that are acting to release the capsule, and from what I can tell, they're going to drive those linkages inboard, which is going to push the clamps outboard and release the capsule, and I guess the acceleration of the vehicle is going to let it drop out of there. Is that's how that's
Yes, sir.
operating?
Yep.
Okay. So you've got two independent motors Are they redundant? If only one activates, will the capsule be released, or do you need both of them to work?
No, sir, you would in fact need both of them.
Okay, is there maybe a way to simplify that? Because needing to rely on two separate systems working is sort of added complexity.
There would be. During the design process, I decided to reduce the vertical space at the top, and then 'cause I did initially look at that, and then I ended up just picking something that was perhaps easier to design, harder to master. So there absolutely would be a way to make that one drive.
Yeah, I would say one drive would be nice. It would cut weight if you could eliminate a motor.
True.
Although the second motor, if you could figure out a way to get it to release, even if only one motor actuates, now you have a redundant system, right? And redundant systems are heavy and they carry penalties, but they also ensure reliability. So maybe that's a worthwhile trade-off. But having two systems that both need to operate in the same way to do one thing is sort of like the worst place to be on that trade. Okay, so now to slide 18. All right, so here it looks like we're doing a yield analysis. Is that correct? I sort of backed out a factor safety on this slide and hitting 1.15.
Yes, sir. So I decided to focus on the yield of the tabs themselves.
Okay. So I would say, as a general rule of thumb, most aerospace materials tend to have ultimate strength to yield strength ratios such that if you're using kind of standard 1.15 yield factor safety and 1.5 ultimate factor safety, they tend to fail in ultimate, right? So if you're going to show one analysis or the other, the ultimate analysis is probably the one to show. For a margin of safety of 150, not a concern. But this one and the subsequent slide, I would say, of the two, if you're only going to show one, ultimate is the one to show there. On slide 20, but I will say I do appreciate you kind of considering that multiple failure modes might have independent factors of safety. So that's I think some good progress from what we'd seen previously. Slide 20, we were talking about the thermal analysis. I don't know that I believe that your capsule exposed to the sun is going to remain within a tenth of a degree temperature range. Like I don't know. Like, are you treating the rest of the vehicle as a heat sink at 50 degrees Kelvin, or like where does that 1200 watts go?
Yeah. So I also agree with you. To be honest, when I first did this calculation, it kind of shocked me, but the numbers checked out, and I did go to the heat transfer professor, and I do know that the correct way to go about this is to look at it from a energy balance perspective, and do an energy balance on the outer wall, and the variable that you're trying to solve for is that outer surface temperature, but yeah, whenever it came up to be 50.1, like that 0.1 difference, I was like, okay, that's a little weird. But it did start to make sense to me because like I said, that emissivity of that aluminum is so tiny. It barely absorbs heat, and it also barely insulates heat. So that 1275 watts, so that is the solar irradiance times the area, and that's what's going into the capsule. And then I am one of the, okay, so there are two assumptions that I made. One, convection is not a factor, and
I think that's a pretty good assumption.
Yeah, and number two, the internal temperature of the lower capsule with the air in it, which is the critical area, because obviously if that temperature increases, the pressure increases, which messes with the dynamics of the release. So I assumed that the inner wall temperature before being exposed to the sun is in equilibrium with the air temperature. So that 1275 watts is going into, well, the entire capsule, but specifically the part of interest is the bottom chamber of the capsule. And then just as quickly as it's going in, it is going right back out due to radiation and conduction.
Okay, so what I'm thinking, and I'm not a heat transfer guy by any means, so I might be way off base, right? But I know I've been doing some work on my car, right? Now, so I've got some bare metal, and you have it parked in the driveway out in the sun, and you go to touch something, and things get substantially more than a tenth of a degree hotter, right? I mean, I think we can probably all relate to that, right? You have a piece of metal sitting out in the sun, you touch it, and it's going to be noticeably hot, if not, burn your hand, right?
Right.
Right. So I don't know that this passes the eyebrow test.
Yeah, I see what you're saying.
Yeah.
I think
it really seems like if, unless
I can definitely
you're
see that.
treating something as like a giant heat sink for you, which I mean it may be, that may be a reasonable thing to do, is assume that you're just so good at transferring heat away from this into the rest of the vehicle, which has the capacity to radiate it away. Like maybe that's a reasonable thing to consider, but it sure seems to me like if this is out in the sun, it's going to get substantially warm, and if it's on the backside of the vehicle, if it's in the shade, right, it's going to get substantially cold. I'll say, like, I don't know a ton about spaceflight, but I do know that thermal management tends to be a pretty massive problem. You look at something like the James Webb Space Telescope, and granted they're trying to get to much lower temperatures than what you've got here, but they go to just a lot of effort to do that, because there's nowhere for the heat to go, right? I mean,
Right.
because you're right, you don't have convection to carry that away,
Right.
so you're effectively stuck radiating away from somewhere. And that somewhere is going to be, somewhere on your vehicle, and you'll conduct it to wherever that is that's effectively radiating away. But I just don't know that you'll be effective enough at maintaining the temperature just passively like that. And again, it's not just a high temperature; it's a low temperature as well.
Right. Yeah. And I would say that you're probably correct, because like you said, the thermodynamics of just space operations in general is a big task. And this is definitely probably an oversimplification. And yeah, I definitely understand with like the just the thought of like, oh, my car's been sitting outside. It's definitely going to be more than 0.1 Kelvin more than it was before it hit the sun. I think, yeah, I think that like the one thing, like you said, which may be a good assumption, from the research that I've seen, it could be a decent assumption that this specific aluminum at the solar irradiance and the solar wavelength that I picked, which the solar wavelength, so emissivity is a function of like the specific wavelength that is hitting the material. And I went with like the kind of a green range in the electromagnetic frequency. And that because that's where it tends to maximize as far as intensity. And essentially what I saw from several research papers is that in this vacuum environment, things like this metal are very good at just kind of like like pretty much like heat passes into it and then it passes right out of it. But then again, that 0.1 increase is definitely would need to be double checked.
Yeah, so a little suspect. So okay, so is that so the tarps? So I know a month ago we talked a little bit about the tarps, and I didn't see a whole lot extra about the tarps. And I think Rick was onto something when he was asking, how do you know how it's going to deploy? Is it going to deploy symmetrically? And when you said, okay, we've got a pressure inside this that's going to blow the quadrants of your capsule out uniformly, that may or may not be the case. And I think, you'd find with testing that things may not quite release exactly like you think they will as they're coming off of the locking mechanism. But what I think is really going to throw things off is you've got a tarp that's folded up inside this capsule, right? And so it's going to be dragging across itself as you're spreading it out. And I think that's going to throw off the dynamics of the release. And then the other thing that I think is going to happen is once it gets to kind of the full extent, it's going to bounce back to some extent, right? Like, so you've got it, kind of flying out at whatever velocity, and all of a sudden the tarp gets taut and it springs back and it pulls things back. And so you wind up with, something substantially less than a fully extended tarp.
I just want to say, sorry, the way that the can is like designed, like the 4 sections, the way that it connects that little thing in the middle, like the wheel rotation, there's like a pin and this one part that connects in. Basically, the way that it goes, like it cannot like come out of that, like it can only like move out of it like in a lateral direction. Like it can't like, there's no way for it to like, come off in a, like, I don't know, like to go down or something. So when the pressure, when it unlocks and the pressure is applied, like it can only like go in a lateral direction. Like there's no, like the way that it's designed, it cannot like move in any other direction. So that's how we are, that's why we're assuming that it definitely is going to move outwards. And it's not exactly like folded up in the middle. It's more like draped, kind of like it's like hooked onto like the top, and then the rest of it's just kind of hanging in there like a little stuff. I mean, it would still probably drag, but that's why we assume that it's definitely gonna extend. Like since we're assuming that it's applied equally the pressure and it can't move in any direction other than the lateral direction.
Yeah, I think you'll find most of the time when people want things to separate with pressure, there's like a rupturing that they take advantage of, right? And any kind of like mechanical release is going to release maybe a little bit slowly. It's going to allow things to separate apart, and all of a sudden you're losing a lot of the pressure that you thought was going to propel you. And things, again, with that sort of, the friction between the mechanism and the canister, I think you'll find that it doesn't quite work out the way you would expect it to. You also have to, consider now you have to seal things, which I didn't see any sort of provision for, but that's that's something that could certainly be accommodated. But yeah, I kind of question the release dynamics and the spreading dynamics. I think would merit a substantial amount of testing of some sort, maybe testing, modeling, and maybe that's beyond the scope of the project. But I think before this would be accepted as a system, I think you'd need a substantial amount of just proof of concept stuff with that sort of deployment mechanisms.
Yeah, right.
And then
I understand.
Yeah. Okay, and so the one other thing I'll throw out here is your cost of materials. Two things. So when Rick said, okay, so you've got a $160 million budget and you're spending $21,000 of that, right? So what are you doing with the other $159.99 million?
I would assume that most of it goes to very expensive manufacturing.
Okay.
For example, the tarp was mentioned, where it's like, like what if they don't have that specific thickness or what have you, and you could say that for in any part of the system. A lot of that would probably come from the manufacturing and the labor to actually make the parts. And in addition to that, testing. Because like you said, especially like the dynamics of the whole thing really need to be tested. I would also say, along with the thermodynamics of the tarp itself being exposed to that exhaust heat for X amount of time.
Yeah, I think that's definitely another part of it.
Now, right. And to estimate that cost, frankly, we don't really know how. We just assume that the other $159,980,000 that $1 million that we have left would cover it, but we could be wrong. Pretty much. Do you have anything else to
Okay.
say?
Yeah, just essentially you're looking at one line item here. You're looking at a single order, could be a qual build, could just be a manufacturer build, but it's yeah, there's some information missing here. So apologies for a lack of clarity there.
Yep.
No problem. I think that's a pretty good answer, right? I mean, one other thing you'll find is the cost of materials is going to balloon, right? These aren't things you go and order from McMaster for crewed spacecraft. So
Right.
even your $21,000 in materials is probably going to balloon substantially. But yeah, I mean, when you talk about labor, when you talk about especially testing, now we're talking about millions. So I think the only thing I would say there is it would be worthwhile to at least try to estimate that in some way.
Okay.
Maybe that means talk to somebody in the industry. I would say if you can get a hold of Mike Generali, he can probably guide you to a number on that. And failing that, anything you can find that's publicly available budgets for any kind of space system, right? Just a ballpark number would at least get you in the the realm of something rational there.
Right. My apologies. We definitely should have.
Yeah, no problem.
Gave at least a rough estimate, like you said. But yeah, that's a good point though. Thank you.
Okay, that's all I got written down,
Sweet.
mostly.
Thank you.
Yeah, thank you guys very much for listening. Mhm. Was there competition? I thought it was Wednesday.
I can't make it, but I've got it.
Okay.
Not everybody needs to do that, if other things can be there, it's fine. You just need to make it closer in advance. Yeah. Do that one. So it's first and. Yeah. So not everyone needs to do that. I don't think like this. Yeah, and we print, so. My wins of repetition with anything else. I will post an announcement, so, you guys can go to my memory and I will go through every order poster with print in my account. So. You're going to pay for printing, so. And I think there's at least this one for their confirmation. Why they push out. And I can go there.
I gotcha.
Yeah, 55 to 2. One is graduate, everybody has their own research.
Right.
And they always want to go there to put something in the resume or something. But undergrad, not many undergrads even have their research. That's why they're like, hey, there you go. So I thought it's kind of chance to post something and the resumes. And not everybody treated. Yeah. Thank you.
Thank you. Cool. All right, do we just kind of log off here?
Yeah.
Did they leave? Thank you guys.
Yep. All right, it looks like we're done here. So thank you both so much for attending today and thank you for your support. We'll get that stuff compiled and the year of the bang. So thank you both. Oh wait, actually wait.
Is there another team going after you?
Yeah,
guys?
there is. I just remember that. My bad. Yep.
Okay.